Assalamualaikum and hi everyone. I am Dr. Hadi from the Faculty of Electrical Engineering, University Technology Malaysia. In this first module, we'll go over the introduction to digital systems design and SystemVerilog. So in this video, we will talk about the introduction to digital systems implementation for ASIC and FPGA design flow, why we use SystemVerilog, who the course is for, and some final remarks on UTM digital badge and credit transfer, as well as the topics that we'll cover in this 14-hour course. Digital chips and systems can be found everywhere around us, with an expected market value worth in the order of billions of dollars. These chips are typically implemented in ASIC or FPGA technologies. ASIC, or application-specific integrated circuits, are basically customized chips or ICs with fixed functionalities. That is, the functionality of the chip cannot be changed once it has been fabricated, for example, Intel and AMD processor chips. On the other hand, field programmable gate arrays, or FPGAs, allow designers to program the chip for both prototyping ASICs and also for deployment. Some of the major companies that produce FPGA devices include Intel Altera and also AMD Xilinx. Now, digital systems are typically specified using hardware description languages, or HDL, for example, VHDL, Verilog, and SystemVerilog. So digital systems design can be implemented in ASIC or FPGA technologies, and each has its own advantages and disadvantages. So looking first at ASIC technologies, they are basically hardened chips, and therefore it provides a fixed hardwired functionality that provides the best in terms of power and performance. However, ASICs are time-consuming to design and implement, which actually requires full knowledge at the circuit level and also has a very long lead time. As for FPGAs, the main advantage is that it allows quick design prototyping, does not require any fabrication and lead time. However, FPGAs are less flexible at the physical level and therefore results in poor power consumption and lower performance as compared to ASIC implementations. So let's now look at the design flow from system specifications all the way to implementation for ASIC and FPGA technologies. The design of custom digital hardware systems begins with system specifications at high level, typically using languages such as MATLAB, Python, C, or C++. Once we have the system specifications, we can start to define the architectural design, typically termed as the microarchitecture. Once we have the microarchitecture, we can use register transfer level design and verification to specify low-level digital electronics and systems, including both combinational and sequential logic. And this is where we use SystemVerilog to specify our RTL design. The next step is to take the RTL design and perform synthesis to obtain the gate-level netlist for the design. And once we have the gate-level netlist, we send the design for physical design, where the logic components are placed and the interconnections are routed. The final step for ASIC, we send the physical design for chip fabrication, while for FPGA, we can simply program the design into the FPGA device. So why do we want to use SystemVerilog for register transfer level design, or RTL design? Well, basically SystemVerilog is the state-of-the-art RTL design and verification methods. It is widely being used in the industry today. It also has been standardized as the IEEE 1800 with a stable release relatively recent in 2018. So how did SystemVerilog came about is mainly due to two key issues facing digital system designers nowadays, which is number one, designs are getting very large and more complex, and number two, verification test benches are growing larger and larger exponentially. SystemVerilog provides new design constructs that are relevant to complex design and verification tasks today. On the other hand, Verilog is relatively limited in functionalities as compared to SystemVerilog. So who should take the course? The course is actually intended for students and professionals, including lecturers, scientists, engineers, and technicians, with basic knowledge of digital systems who wish to learn and explore the capabilities of SystemVerilog in digital systems design. The course is also aimed at students who wish to obtain a master's degree for the course and obtain a credit transfer for this micro-credential course. Besides that, experienced engineers with knowledge of Verilog will also benefit from the course, especially for those who wish to upgrade their knowledge and skills in SystemVerilog. And finally, the course is in fact for anyone who wishes to learn state-of-the-art methods in designing digital systems. So here is the learning flow of the course. We'll have a total of 8 modules with a total of around 14 hours of learning time. The completion of all the 8 modules in this micro-credential course gave participants a UTM digital badge. So as you can see in the flow chart, the flow of the course begins with watching a video module and do submit the learning activity. The learning activity is self-assessed, so you perform self-assessment on the learning activity, and once you feel confident with the learning activity and understood the material, you can start doing and submitting the graded assessment. Once you have submitted the graded assessment, you will get feedback from myself, and if you pass the assessment, you can proceed to the next module. However, if you, in the case that you have failed the assessment, you may retake another assessment and get a second feedback from myself. And once you have completed all the 8 modules in the learning flow, you can then apply for a UTM digital badge. The course is in fact a part of 3 micro-credential courses, and this current course is called the SystemVerilog Fundamentals for Digital System Design. The second course, after you have completed this course, you may take the second part, which is Register Transfer Level Design or RTL Design and Optimization with SystemVerilog. And the third in the series is using Xilinx Vivado High-Level Synthesis for rapid prototyping. The completion of all these 3 courses enables credit transfer to MKEL 1283 Hardware Software Co-Design to our UTM Master of Engineering Computer and Microelectronic Systems program. So these are the topics that we'll cover for the 8 modules with a total expected learning time of around 14 hours. So module 1, which is the current module, is on the Introduction to Digital Systems and SystemVerilog. In module 2, you will learn about the basic and intermediate constructs in SystemVerilog, including how to represent numbers, operators, and how to declare data in SystemVerilog. In module 3, we'll cover the modeling styles in SystemVerilog RTL, including some practical examples of designing circuits such as the multiplexers, the adders, and also the tri-state buffers. In module 4, we'll cover modeling sequential logic in SystemVerilog, including D flip-flops and registers. Module 5 will cover memory design and parameterization. In module 6, we'll cover finite state machine design in SystemVerilog with also some practical examples of FSM designs. In module 7, we'll cover test bench design for verification, including SystemVerilog self-checking mechanism. And finally, in module 8, we'll have a hands-on tutorial on using AMD Xilinx Vivado for design and verification. Note that for module 1 and module 8, there will be no learning activities and assessments. Therefore, you are only required to do the learning activity and assessment for module 2 until module 7. So with that, we have reached the end of this video. If you have any questions, do not hesitate to write them in the comment box below. Thank you and see you all in the next module. Bye.